In this video, we're going to introduce resilience modeling by defining grid outages and options for serving or shedding loads during outage. This video uses the basic single-node model constructed in the previous tutorial video. If you are following along with your own model, I'd recommend going back and working through that video first. In the previous video, we conducted a pure cost optimization with the option to invest in solar PV, conventional battery storage, cold thermal storage, and several CHP units. We also forced investment in a single 65 kilowatt CHP unit. Our optimized model selected 362 kilowatts of new PV capacity, 344 kilowatt hours of cold thermal storage, and selected no battery capacity and no DG units beyond the single unit we forced it to deploy. This design solution produced a total annual energy cost that included amortized costs for new DER investments that was 33% below the reference, and a CO2 savings of 52%. Given this as a blue sky design solution, when grid electricity is always available, let's see how the design changes when outages are introduced. To do this, let's take our existing model and navigate to the resilience menu. The first step is to add additional outage design days. Let's add an emergency weekday day type to both June and December. We'll be sure to reduce the number of weekdays by 1 in each month to ensure we keep a total of 365 days. Next, we'll define the outage and what are labeled in DIRCM scheduled outages. Scheduled just means we're explicitly scheduling and modeling a grid outage, and is the option used for resilience modeling. The unscheduled outages option uses a probabilistic model to determine reliability value related to shorter duration outage events, which isn't what we're trying to model here. Within the scheduled outage table, we use a binary value to indicate the hourly availability of the grid for each emergency day type. Since we've added outage days for June and December, let's go ahead and zero out the grid for each of these days, which indicates full 24-hour outages. With these changes made, we're ready to save and run our initial model. Results show investment in additional PV capacity, new battery capacity, and reduced investments in cold thermal storage relative to the previous blue sky investment case. Looking at the dispatch results page, we can see how the system uses PV, buffered by storage and DG to serve the full building load during the outage event days. This design solution also produces smaller savings to annual energy costs of only 14%, indicating that a design that is resilient to these two full-day outages comes at a cost to overall economic performance. We'll discuss in a later video methods to quantify the monetary value of resilience, which this particular model doesn't currently include. Before we do that, let's introduce the option to curtail loads. In some cases, critical loads can be isolated and served separately from non-critical loads. In the event of a grid outage, such buildings would have the option to suspend service to non-critical loads to increase the duration or reduce the capacity necessary to preserve critical operations. To add this ability to our model, let's navigate to the Load Curtailment menu. Here we have the option to define different levels of curtailment, each with a cost, curtailment amount, and maximum number of hours it can be used per year. For this case study, let's add a low priority curtailment option consisting of 25% of electrical loads, which is free to deploy, and another 25% medium priority level with a use cost of $1 per kilowatt hour. We want to limit the use of curtailment for outage events, so we'll define the maximum hours to 48, corresponding to our two 24-hour outage design days. This means the model can freely curtail 25% of its electrical loads, and another 25% if it's economically optimal, but it must serve the remaining 50% of loads, which represents our site's critical load level. With these changes made, we can again save and run our model. After the solution is returned, we see a solution much closer to our blue sky optimal design, indicating that demand-side management, in this case curtailment of loads, is an economically valuable resource when paired with conventional DERs. Its inclusion in DIRCAM gives users a lot of flexibility for building their system models and helps explore the trade-off between different levels of resilience and the resulting economic performance of the design solution. Before closing, I want to point out that both of these resilient designs were able to produce cost savings versus the reference case with no DERs. This isn't always the case, however. In instances where grid electricity is inexpensive or DER capital costs are high, it's easy to find yourself with a system where adding resilience increases overall costs. Depending on how you've set up your model, this can produce an infeasible result. To help navigate this potential obstacle, in the next video we'll introduce methods to quantify the monetary value of resilience using the load curtailment option and a value of lost load metric.